for this lecture. So the last concepts in this chapter. So let's relate the E0 for the cell to equilibrium constant K. And then the last concept will be what's known as the Nernst equation. So how does the cell relate to concentrations of everything involved in the reaction? Okay, so for E cell and equilibrium constant, so in this chapter 19 we saw this equation delta G equals negative NFE, and in chapter 18 this equation delta G is equal to negative RT ln K. So let's combine those two equations. So negative NFE 0 cell equals negative equals negative RT ln of K. So the negative sign cancels. So NFE 0 cell equals RT ln of K. And if we solve this for E0, equals RT ln of K over NF. And if we convert natural log to logarithm, then we get that equation. And then we can simplify this a little bit further. So at 25 degrees Celsius, so we can substitute in for T. Of course, we need to convert that to Kelvin and then substitute in. And so at 25, I'll substitute for T. F is a constant, R is a constant. So if we make all of those substitutions, so E0 cell then is equal to 0.0592 log K over N. Or if we solve this for K, then K is equal to 10 to the E0 cell times N over 0.0592. So it's a simple calculation then, so you just need to be able to figure out if you're given K, take the logarithm of the equilibrium constant divided by the number of electrons in the balanced cell in the balanced half reactions, and then you have E cell. Or if you want to figure out the equilibrium constant, right, then if you have the two half reactions, calculate what E is, figure out what N is from the two half reactions, and then you can calculate K. Okay, so let's take an example. So what is K for this oxidation reduction reaction? So iron 3 plus copper 0 to make iron 2 plus copper 2. So we need to write the two half reactions because you have to figure out what N is. So if we write the two half reactions, so Fe3 plus an electron goes to Fe2 plus, and copper 0 goes to copper 2 plus 2 electrons. Okay, so we need to figure out what E is, and we need to figure out what N is. Okay, so this is a reduction. So this you'll find in the table. So the reduction potential, so 2 iron. So if we wanted to balance this equation, then we need 2 iron and 2 electrons to make 2 iron 2. But that doesn't change what E is. It's 0.77. And for copper to go to copper 2 plus copper 0, that's not in the appendix. What would be in the appendix is copper 2 plus 2 electrons to go to copper 0. So E for that is 0.34. So E0 cell would be 0.77 minus 0.34, 0.43. And so this would be negative 0.34. Of course, you could also just take the original two half reactions and add them together and get the same answer. Okay, so now you have, so N is equal to 2, right? So we have two electrons, two electrons in the balance half reactions. And we have E is 0.43, so we can just plug into the formula and solve for K. So K is equal to 10 to the 0.43 times 2 divided by 0.0592 is equal to 3.4 times 10 to the 14th. Okay, so a huge equilibrium constant, so this reaction would lie very far to the right. All right, and then the last concept in this chapter that we'll look at is cell potentials and how it relates to concentrations. So if you had a cell set up, for example, like this, so you have M2 plus, some generic, whatever the metal is, if you're working with a metal, 2 plus, so that's at a certain concentration. And we'll just call this X and X2 plus, so whatever X is. So these are at some initial concentration. Of course, there has to be some or the cell can't work, right? If there's no X2 plus, so let's say the electrons are moving this way. So M was giving up electrons to make M2 plus go into solution, and those two electrons go on to X, whatever X is. If there's no X2 plus in solution to begin with, then there's nothing to pick those electrons up, so there's no voltage. So there has to be some M2 and X2 to begin with in order for there to be a voltage, in order for there to be a current. But as this reaction proceeds, then the concentration of M2 plus and the concentration of X2 plus is going to change, right? So M2 plus is going to go up. Well, so, and X2 plus is going to go down, because X2 would be, if the reaction's working right to left, X2 plus would be picking up electrons and coming out as X0. So the concentration of X2 would be going down and the concentration of M2 would be going up. But the point is, over time, their concentrations are going to change, and so how much is present in solution at any one time is going to affect what the voltage is. And so this relationship between the cell potential and the concentration of the reactant species leads to what's known as the Nernst equation. Okay, so this would be the so the Nernst equation then. So E for the cell is equal to the maximum value of E minus RT over NF ln of Q, where Q is a reaction quotient. So it's equal to concentration of products over concentration of reactants. So as reaction proceeds, of course, concentration of products is going to go up, and concentration of reactants is going to go down, which means Q is going to get bigger. So as reaction proceeds, then this term gets bigger. Which means So the voltage that you read goes down, right? Eventually, if this was a battery, eventually the battery would be discharged. There would be no voltage anymore, right? So that makes sense because eventually there would be no more X2. If X2 is constantly coming out of the solution, eventually it goes away, and then the reaction has to stop at that point. Okay, so again, we can simplify this equation as well. So at 25 degrees Celsius, plug in R, plug in F, which are constants. So then the voltage that you measure would equal to the maximum voltage possible, which you can calculate using the appendix I, minus 0.0592 over N log of Q. And if we change natural log to logarithm, then we come up with that equation. So that'll be the equation that you have to know how to use. Okay, so let's take an example. So let's calculate the cell potential of the following cell at 25 degrees Celsius. So if you're given the shorthand notation for the cell, then you should be able to sketch what the voltaic cell would look like. All right, so you got chromium and chromium-3. So chromium would be given up 3 electrons to make chromium-3. And where those 3 electrons would be going over to the nickel electrode. And so nickel would be picking up electrons and coming out of solution as nickel 0. So you're given an initial concentration of chromium-3. And you're given the initial concentration of nickel-2, which is 1.5 molar. Okay, so now what's a product? What's a reactant? So if you write the chemical equation, so chromium gives up 3 electrons and becomes chromium-3. So chromium-3 is a product in this reaction. And nickel-2 picks up 2 electrons and becomes nickel 0. So nickel 2 is a reactant in this problem. Okay, so we need to figure out what N is, right? So we need to figure out what N is. And we need to figure out what E0 is, and we're given values so that we can plug in for what Q is. Okay, so we need to write the 2 half reactions. So chromium 0 goes to chromium 3 plus 3 electrons. So that is an oxidation. So you won't find that value in the table, but what you will find is chromium 3 plus 3 electrons to go to chromium 0. So that you'll find in the back of the book in the appendix, negative 0.74. So this will be a positive 0.74. And then nickel 2 plus 2 electrons goes to nickel 0. So that's a reduction. So you'll find that in the back of the book. So that is negative 0.23. Okay, so E0 cell. So if we calculate it that way, then we need this equation, and that one, the original half reactions. So you would get negative 0.23 plus 0.74, so 0.51. Or if you use the other equation, E cathode minus E anode, then you need both reduction equations, right? So then you need that equation and that equation, both reduction equations. So negative 0.23 minus a negative 0.74, and you get 0.51. Okay, so that's E, and now we need to figure out what N is. So you have to have a common number of electrons between the two reactions. So obviously what you need to do is, let's take these again. So if you want a common number of electrons, the common number is going to be 6, right? So you got to multiply everything here by 2 and everything here by 3. Right. But again, that doesn't change what E is. So so N is 6. Okay, so now we can solve this problem. So E0 cell was 0.51 minus 0.0592 divided by 6, and then log. So Q is going to be products over reactant concentrations. And we said that nickel 2 is a reactant and chromium 3 is a product. So it's the log of 1.0 times 10 to the minus 3 molar over 1.5 molar. And then calculate that out. You get 0.54 volts, because this is volts. Okay, so that's what we wanted to do. Calculate the cell potential of that following cell at 25 degrees Celsius. And so it's 0.54 volts. Here's your answer. And that's how to use the Nernst equation. Okay.